But all right, so on 37 we have this. So I kind of did this. You don't have to do it that way, but this is basically the idea that if it's going to be an odd function or have origin symmetry, then when you put x, y in, or the original equation should be the same as if you put negative x and negative y in. Okay? If you put this in, then that's going to be your y-axis symmetry. If negative xy is the same as xy, and then this one is going to be x-axis symmetry here. And it's pretty easy to tell which one's which, because if you have xy, if you have the point xy, and you put in x negative y, right, that's going to be x-axis symmetry. Okay? If you have the point xy, and you put in the point negative xy, right, that's going to be y-axis symmetry. And then, of course, here, if you put in the point xy, and then you have the point negative x, negative y, that's origin symmetry. Okay? So you can keep those two straight. So, Kale, what was your question on this one? Just didn't work out. Okay, so let's take a look. So if I put in a negative y here, and I put a negative x in everywhere there's an x, this would be negative x squared plus 1. I would get negative x over, then this would just turn to positive, like so, and that'd be negative y. Now what I would typically do here is divide or multiply both sides by a negative. So if I multiply both sides by a negative here, what does that do? Well, multiplying by a negative is kind of like doing this, right? Negative 1 over 1. I mean, if you multiply this by a negative, you're not going to multiply the top and the bottom by a negative, right? You just multiply really just the top, essentially, by a negative. Okay? So this would turn into positive x over x squared plus 1. That could be one of those little things that could throw you off, is how do you simplify this? Well, like I said, dividing by a negative or multiplying both sides by a negative would just turn that to basically a positive, which actually is a match. So we got it. So it's got origin symmetry. Now you might say you probably should check these others, because it's possible that you can have more than one, but only if it's not a function. Like if you have a circle at the origin, that would have x-axis, y-axis, origin, and have all. Okay? Typically, any equation that's just a y equals just a typical equation like this is not going to have that. It's going to have one or the other. So we'll just run through it real quick. So this one, of course, again, you got your original. So we put a y in for the y. We put a negative x in for the x, which we've already seen what that does. It ends up being this. We get y equals this. Well, what do you got there? Is it the same? It's not the same. This got a negative up here with that, so that's no match. And then this one, we put a negative y in for the y. We just put an x in for the x. Of course, put an x in for the x is the same. Divide by a negative, like we said, or times by a negative will just make the top negative. And again, it's the same as that. It's not a match. Yes, sir?
When you find one, you don't have to keep looking, do you?
Well, that's what I was saying. I really think when you find one, let's put it this way. I'm not going to, if I ask you this question on the quiz, I'm not going to, you don't have to do them all, okay? But if I give you one that's got more than one, and you don't check them, right? Now, what's that going to look like? It's probably not going to look like any of these that you saw here today. When you go through this, I mean, as we go through here, this is a sideways parabola, okay? It's got, or no, that's a regular parabola, so it's got y-axis symmetry, okay? This is a sideways parabola. It ends up having x-axis symmetry. Now, on our next quiz, which is going to be Friday, I believe, you will be asked to find x-axis, y-axis symmetry by the algebraic test, using algebraic, which is this, okay? So when you hear me saying, well, you know this is a sideways parabola, so it's going to have x-axis symmetry, if I were to say just use a graph, or if I give you a graph, then that's good to know too. Okay, but right now we're focused on this algebraic way of showing it. I want you to be able to do this. And you're definitely going to have to do that on the next quiz. Okay? This is an x cubed, and so it's going to have origin symmetry. This is an x to the fourth. It turns out that this particular one is going to be, did you get y-axis on 36? This should be y-axis symmetry on 36. This one ended up being just origin What about 38? Y-axis, okay, 39. Which one? X-axis, okay, has a y squared in it. This one is origin, I believe. Okay, so you're right. For about any equation that I'm probably going to give you, there's going to be one. So once you find it, you're good. Okay, I would say most of the time. But then again, if it were me and I was taking the quiz, and I might just check those others just in case. You know what I mean? But I'm probably not going to require that. If you get the right one, if there's just one, and you get the right one with your work, good. That'll be okay. All right. What else? What was the other one? 29. Okay. So what was 29? Find the x and y intercepts. Okay. So we got y equals 2x cubed minus 4x squared. So x-intercepts and y-intercepts. X-intercepts are when you have something 0. Y-intercepts are when you have 0, right? So a y-intercept is when you put a 0 in for x. So that, of course, is easy. That's going to be y equals. I don't expect you to show all this work necessarily, but that's just going to be 0. Right? So that's 0. So the y-intercept is going to be 0, 0. Okay? The x-intercept, we put a 0 in for y. So we get 0 equals 2x cubed minus 4x squared. Now this is why you might have saw the warm-up that I had up here. We're going to do in a minute. Because when you have to find an x-intercept, and to be honest with you, on most graphs, as you'll find in calculus and in even this year, we're way more interested in the x-intercepts typically on a graph than we are the y-intercepts. Because number one, there's only one y-intercept, and it can be meaningful. A lot of times, if it's a story type problem, it's your beginning number, it's your beginning amount, your initial amount. So it can be important, but we're typically way more interested in these values, the x-intercepts. Okay, it's where the equation equals 0. So it's just a matter of solving the equation. So what you do is you just factor out 2x squared, leaving you an x minus 2. So either that or that is 0. So 2x squared is 0 would be when x is 0. And x minus 2 equals 0 would be when x is 2. So it's just that. It's just solving the equation. Okay, so we have 0, 0, which we already knew from there. And then we have 2, 0. So there's our x. That make sense? I mean, which part, Jack? You still look.
I got it.
Got it? Okay. All right. All right. So those are some things on our next quiz you probably have to do. Here's an equation, x-intercept, y-intercepts. We're probably doing some solving. Symmetry with that algebraic test. Those are the main things out of here. Okay. All right. Well, let's spend a little time then on that very thing right there, since that's kind of a big deal. If you got to find x-intercepts of a function, which we're going to have another name for that as we talk about functions today. So let's go ahead and just practice this solving stuff real quick. Can I put the answers up here? Yes, sir.
Number 5 should not be -3 instead of -2.
5 times 2 doesn't equal 15 anymore?
No.
It's 5 times 3, I see. Used to be if 5 times 2 is 1.
Gotcha.
Back when I was in school. Thank you, Zach.
No problem.
Did anybody on number 4 try to divide by x on both sides?
And maybe you don't want to admit it.
Okay. And you got to be careful there. You can, but what's the problem with dividing by x? What's the problem with dividing by x then? Then you get x equals 4, right? You divide by x on number 4, divide by x is gone on this side, you get x equals 4, and then you lose that one solution, right? And you don't have to lose it, because when you divide by a variable, right, it's illegal to divide by what? You can't divide by 0, right? You can't divide by 0. So if you divide by a variable, if you divide by x, you could potentially be dividing by 0. So what you have to understand is if you divide by x, that equation that you get, you may have lost that solution where what you're dividing by could be 0, right? Like if you divide both sides by x minus 4, right? You've just lost x being a 4. Or if you divide by x plus 2, you've lost the situation where x could be a -2. So you've got to think about that. You got to say, okay, in the original, was that a solution? And so in this case, if you divide by x, you're like, well, that eliminates x being a 0, so I better check the original. Could x be a 0? And sure enough, x being a 0 works. So it's okay to do it, but to be honest, I would try to avoid that. I would try to avoid dividing by a variable when you're trying to solve, because a lot of times you forget about that part. So what we want to do is get 0 on one side, solve it, and do that. Okay, and then on this one you could factor, or on this one, you'd have to FOIL this together, because remember we talked about that the other day. 2 things multiplied does not mean one of them equals -3. That only works with 0. Okay, so you've got to get 0 on one side before you can do that. Okay, so you've got to FOIL this back together, get x squared minus 4 equals -3. Then you can either add 4 over there and get x squared is 1, square root both sides be plus minus 1. Or you can add the 3 over to here, get x squared minus 1, and then factor that. X plus 1, x minus 1. Either way, you're going to get plus or minus 1. Okay, so that's just some review on quadratics and factoring and that kind of stuff. And that's something we got to be able to do. Those things show up from time to time. Now here on this one, on 6, I went in and divided everything by 2 on both sides because that's okay. I'm not dividing by 0, so it's okay to divide by 2 and get that out of there, and it just makes it work a little easier. Okay, let's go to your notes then. Well, this is going to be section 1.4. We're going to, a couple things probably to jot down here, a couple of examples, but most of this should be review. Okay, so we're going to go pretty quickly here. Matter of fact, most of this whole chapter, this first quiz, should really be, a lot of this stuff is a lot of review. So I just want to quickly touch on linear equations. This is section 1.3 in the book, but we're not going to spend much time on it. So linear equations, you spend a lot of time in algebra 1 and a decent amount of time in algebra 2, and so we don't do it a lot, which is funny because I always notice my calc students, one of the things we struggle with in calculus is going back to linear equations for some strange reason. And maybe that's because we don't spend a lot of time in here in this class on linear equations. So all of a sudden you get to calculus, it's been a while. And so just a reminder, and I think Mrs. Andreessen does the point slope form the bottom way. I think you guys did this in Algebra 2 for point slope form. A lot of books have point slope form written this way, but I always, Ms. Andreessen and I a long time ago decided it's much better to just add that y1 over to the other side and write it this way. Does that look familiar? Does this bottom one look familiar to you? Okay. Well, if it doesn't, memorize. I mean, but here's why. I'm not going to get into it right now, but the reason you'll see the reason why on actually what we're going to talk about the next couple days as we start talking about transformations and moving graphs around and so forth. Plus, we like to have y by itself. We're writing equation, we like to have y equals. So it just makes sense to write that over there. So your book, our book here, uses this form. So when it talks about point slope form, because, well, I'll just show you. Let's do a quick example. Okay, so do that real quick. Find the equation line through these 2 points. Okay, find the equation line that goes through those 2 points right there. Taylor, what do you got?
I haven't guessed yet.
Okay. Lucas, what do you got?
Not quite down.
Chloe, what do you got? I should give you more time then, shouldn't I? 3 strikes and you're out. Caleb, what do you got?
Y equals negative x plus 5.
Y equals negative x plus 5. Okay. How'd you start, Caleb? What'd you do first?
Well, I figured out what the slope was. I did like the y minus y over x minus x.
Okay, so before we can find the equation of a line, we need a slope. We need to know the slope of the line, right? So if you're given 2 points, so the first thing we have to do is find the slope. Okay, we have to find the slope of that line. Okay, so that's -1. And again, I say this over and over in calculus. We just did a problem today in calculus about finding the equation of a line that was touching a certain curve. And so what we had to do is, and again, I'd say it over and over to them. What do you need to find the equation of a line? You need a point and a slope. You need a point and a slope. So if they give you 2 points you find the slope first, and then pick one of those points, okay? Now, there's two ways to do it from here. Now, I think Mrs. Andreessen uses the point slope form all the time. There was a time when there was different teachers, different Algebra 2 teachers did it differently, different Algebra 1, different books taught it differently. So I'm just going to show you both, and you guys tell me what you've seen before. But one way would be to just use y equals mx plus b, okay? So one way would be to take, I took this point here, put a 3 in for the y, put a 2 in for the x, put a -1 in for the m, and find the b. You ever remember doing that? Now, to be honest, I don't like doing that. That's my least favorite way to do it. But that's one way to do it. Maybe in 8th grade you did it that way. I don't know what the 8th grade teachers teach if you had Algebra 1 in 8th grade. But you end up with b equals 5, so your slope's -1 and your y-intercept's 5, right? Or, and this is the way I teach it in calculus, is we use the point slope form. Now, the reason I really like the point slope form is in calculus, and you might be surprised, you think calculus should be harder. I can't believe they'd let you off the hook like this. In calculus, when we have, on the actual AP calculus test, if they ask for the equation of a line, it is perfectly legal to leave it right there, like that, okay? Now, I'm probably going to go ahead and say to simplify it if we run into this, you know, if we do a problem like this, but so like I said, if the AP test in calculus, if they're going to let them leave it like that, then what the heck? Why go through all this? You know, all you got to do is plug in your slope, plug in your point, and you're done. Right? Now all that's left is to distribute and finish it, but it's pretty much the same thing. Okay, so that from algebra class is something we want to be able to do with linear equations. Okay, all right. So now moving on to the main so that was what section 3 was about, with just linear equations. We're not even going to do any of the homework for that. We're not going to spend a lot of time with that. We will talk about graphs of lines at the end here in a little bit. Okay, so let's talk about a couple of definitions that we want to get written down here before we go to lunch and get a couple other things down. So a relation. Okay, and I know these are some things you spend a lot of time in Algebra 2 talking about. Function for sure, okay, but first we want to define relation. A relation is when quantities from two sets are related to each other by some rule, i.e. it's a set of ordered pairs, okay? A set of ordered pairs, two quantities, usually we use x and y, okay? But it doesn't have to be x and y. We can use other letters, but typically, you know, the more common one is x and y. And they're related to each other somehow, and so therefore the name relation. And I just put an example of one here, and I showed it with a kind of a mapping with boxes, and I showed it with a set of ordered pairs. So 1 is paired with 2, and 1 is paired with 3, and 2 is paired with 5, and 4 is paired with 5. And so if you drew a picture of it, like in a box, this is your domain, and this is your range, and those are some terms I know you're familiar with. Now sometimes I will talk about input and output. Okay, domain and range, input and output, those are somewhat interchangeable. This is typically also sometimes known as the independent variable and the dependent. And one way you can help remember those is input and independent are together, input and independent. Because typically with a relation you can plug in any number and then what you get out is dependent on what the rule is that pairs them up. Okay, so the independent variable, you can plug in anything you want. And then the output is dependent on what the rule is that matches those up. Now, some of you are probably already bothered a little bit, maybe, by this first two pairs here. 1, 2 and 1, 3. What's the problem there? not a function, right? Well, we didn't define this as a function, right? We defined it as a relation. But that's where you get a problem if you want something to be a function. We're going to define function here right now. But this is okay. It's okay for 2 to match with 5 and 4 to match with 5. That's fine. Any input can only have one output. So 1 can't match with 2 and match with 3. Okay? Can't do it. But you can get the same output, right? 1 can match with 5, 2 can match with 5, 3 can match with 5, 4 can match with 5. Okay? As long as that's all 1 matched with, and that's all that 2 matched with, right? So any one input can only have one output is what makes it function. So our second definition, function, each element in the domain is paired with only one element in the range. Okay, and so then of the 3 graphs I have down here, which one of those is not a function? It's this one right here. And we had the old vertical line test. If you have a graph, if you can draw a vertical line through it, and it crosses more than one point anywhere in there, then you have something that is not a function. Okay, so this one is not a function. The other 2 are. Okay, the other 2, any vertical line you draw through there is only going to touch in one place. Okay, all right. So let's go through. I just want to. There's a couple of good things here in this PowerPoint. There we go. All right. So I don't know how much of this you need to write down. We'll work out a couple of different types of problems, and I'll talk to you about it. Okay, so that talks about relation. This talks about function. So here would be, so one of the things you'll hear in your homework, or we'll hear today a little bit, is talk about functions verbally. Like here would be a function that relates the time of day to the temperature. And what we would say, how we would say that is, the temperature is a function of the time of day. So when you say that, the temperature is your output. Okay, the temperature is a function of the time of day. So temperature would be your output, and time of day would be your input. Y is a function of X is how we typically have equations written when it's Y equals. Okay, you start with the output. Y is a function of X. And that's because at any given time of day, how many temperatures are there? Right? At 12 o'clock, straight up noon, there's a temperature outside. And only one temperature. Okay? There can't be more than one. Now, it could be that same temperature all day long. You know, at 12 o'clock, it could be the same temperature at 12:01. That's okay. All right? Like here at 3 and 4, they both go to 15. That's fine. Okay? Sometimes when people have a diagram like this, they remember function. You can't have 2 arrows going out. You can have 2 arrows coming in, but you can't have 2 out. You can't have 2 different arrows coming out of here. That's another way to think about it. Okay? So, characteristics of a function, I wouldn't write this down, but it says each element in A must be matched with an element of B. Some elements of B may or may not be matched, right? For example, I'm not sure today it's going to hit 100 degrees, right? So there are some outputs that won't have anything matched to it. That's fine. But every element in A will have something output. 2 or more elements in A could be matched with the same element in B. We talked about that. But an element in A cannot be matched with 2 different elements of B. Okay. 4 ways to represent a function verbally. So we were just talking about that with just in words. We could have a table or a list of ordered pairs. We talk about graphs, or we could have algebraic, which would be an equation. Okay. So we can see functions written all those different ways. Okay, just look at those real quick. A, B, and C, which ones are functions, which ones are not. Input X is the number of representatives from a state. The output is the number of senators. Function, yes or no? What would be the ordered pair for Nebraska? 3, 2, 3 representatives, 2 senators, right? And now think about that from any state. So is it a function, yes or no? Does any other state have, oh shoot, I can't write. Does any other state have 3? Yes, there are other states that have 3. But what would their ordered pair be? 3, 2. So is this a function, yes or no? The only way it's not a function is if you have 3, 2, and then you also have 3, something else. 3, 4. Now, it would be a different state, I get that, but 3, 2. Because what's the output on all of these? The output's always going to be 2. It's always going to be something 2, right? But 3, 2, so there won't be a 3, something else. So I think this is a function. This would be a function. It'd actually be a horizontal line, right? Well, it'd be a bunch of dots, right? Because, okay, but it'd be horizontal. So the outputs would always be 2. Okay, what about B? No, because you got 2, 11, 2, 10. And then C would be, all right? So the verbal, you got to think about the verbal. Okay, those are just the answers. We talk about equations, independent, dependent variable. Okay, function notation. Okay, so when we talk about function notation, so all right, when we talk about function notation, so again, we should all be familiar with the function notation here, okay? And so f of x equals 3 minus 2x. This is not times. This does not mean f times x, okay? We read it f of x. That's different, okay? F of -1, f of 0, f of 2. How do we find f of 2? That's what that means. Plug in a 2 for x, right? So they did it here, f of -1, f of 0, f of 2. That's all easy stuff. Now, keep in mind that we do not have to use, go to lunch. I'll try to remember exactly where I was.
Foul's on 22, Cassie Nash. First personal foul, first team foul at the line, shooting 2, Alexis Fisher. Football, first goal, it's good. Football, first goal, it's good. First ball. It's good.
Left off here.
You don't have to use.
Is that what I'm saying?
Yep.
You don't? Yes. Thank you. I didn't remember that.
Did you start the recording again?
I just restarted the recording. Thank you. You don't have to use X or as your input variable or domain variable, and you don't have to use f necessarily as the name of the function. So f of x equals x squared minus 4x plus 7 is the same as f of t equals this, is the same as g of s equals this, is the same as g of,
Spider.
no, spider? Looking like a spider.
That's a dog.
Close. Yes, it is a dog. It's specifically, it's a German Shorthair. And, right?
Why is it a square?
Well, yeah, somebody once told me, it looks more like a boxer. Yeah, that's funny. All right, but more like a German Shorthair is what, so G of German Shorthair equals German Short squared minus 4 German Short, but 7. It could be that, whatever, right? It's just kind of a placeholder, like they say, or a dummy variable, whatever. It's just G, f of whatever, the input thing is you take that thing and square it minus 4 times that thing plus 7, okay? Typically it's f of x, but it doesn't have to be, so that's important to understand. And so then they kind of give that example then. All right, so next thing, talk about quickly, a piecewise function. A piecewise function. Now, sometimes just because that notation looks a little scary, and you did these, right, in Algebra 2? Does that look familiar? I'm sure you did. But that, it looks a little scary, but it's not. All it does is it says, okay, we're just going to take a graph and do it in pieces, okay? For a while, we'll do this function, and then for a while, we'll do a different function, and then for a while, we'll do a different function, and then put them together. So this is just saying we'll have the parabola x squared plus 1 whenever x is negative, and when x is 0 or more, then we'll switch and be the line x minus 1, right? And so if we were going to graph that, if we want to do a graph of that, you could just plot some points, but it's just going to be, if you know that that's just a parabola shifted up 1, which we're going to talk about shifting and stuff like that later in the week. But if we plotted a few points, we would have that. But that would be an open circle there because x is just when x is less than 0. And then the line x minus 1, which would be y-intercept down here of 1 and be a slope of 1, so up and over and so forth. And so then that would be something. So you would have a graph that looks something like this. Okay, and it is a function, right? Because it passes the vertical line test. So vertical line And then right here, since that's open and that's closed, we're fine, and then we have a line. So that's just a piecewise function. And so if it asks you for f of -1, you would go to the part of the graph where x is negative. And if you wanted to do f of 0, then you would plug into the other part of the equation. So that's called a piecewise function. So we talked about domain. So a term here that is important for you, implied domain, or sometimes I know our calculus book calls it the natural domain. So when you have a function, the domain is all of the inputs. Now, the way to keep in mind that the big two, when it comes to domain, the two things you look for is what? You can't divide by what? 0. And you don't want a negative inside of a square root. Those are the two things that are the kind of the big no-nos for functions when it comes to domain issues. So in other words, if you have this function right here, we know we cannot let x be a 2 because we would not get an output, right? The domain is all the inputs that have an output, an element in the domain that matches with an element in the range. Well, if x is 2, it's undefined. So there will be no matching output. And when x is -2, there'll be no matching output. Okay? Now, really, it would be that you could just do in your head, but what you would do is you'd say, well, we don't want the bottom to be 0, so it's really like solving this equation. You just take the bottom, you set it equal to 0, you could factor, just like we did in our warm-up, and you see, well, x is plus or minus 2. Now, in this case, what we want to say then is, okay, our domain is everything but plus and minus 2. Okay, all reals except plus and minus 2. And that's called the implied domain. If you were given this function, they're not going to say x can equal plus or minus 2. You just have to figure that out from the problem. You just have to know that from the problem. It's implied in the problem, or it's the natural domain, okay, of that. But sometimes we'll do a function, and I might give you the function f of x equals x squared, and this happens in calculus all the time, f of x equals x squared, and the domain is this. And so what we're saying, we'll say something like that, right? And so what we're saying is, okay, we're going to look at f of x equals x squared, but we're only going to look at it in the domain 0 to infinity, right? And so then you're giving a specific domain. But if you're not given a specific domain, then the implied domain is the one you're looking for. Okay? So again, the two big ones are you can't have a negative inside of a square root, and you can't have 0 on the bottom. So let's just talk through these right here real quick. Okay? And if you want to jot them down, you can. It's up to you. But so you're going to have some homework problems like this. Find the domain of this function. Okay? So you're going to have some homework problems that are going to be similar to this. Find the domain of this function. So if it's given to you like this, as a set of ordered pairs, then you're going to say what for the domain. Now, I'm not going to get quite as picky on the language that Mrs. Andreessen had you do, which I know, which is good. I mean, you would probably do something like this, and probably been domain x such that, that kind of stuff. We're not going to, it's good in Algebra 2. I think we make a big deal about that. We write it, we're used to it. So when you see it, you know what that notation means. But for us, when we write it, I'm not going to get that particular. So I'm going to probably say something more like what they have here, domain, just your set notation. What would you write? That's a good brag. What would you write? -3, -1, 0, 2, and 4. You're just writing the x values. Simple as that. Okay, when you have something like that. Okay, on B, what is the domain? In other words, what are we saying? On one like this, we're saying, on this one's easy. What are all the inputs? And they're just listed for you, so that's easy. When you have an equation, the question you have to ask yourself for domain is, what is allowed to be put in for the x? And of course, the easier side of that is actually, well, what can't be allowed? What's not allowed to be put in? -5, because that would cause division by 0. We can put a 0 in for x, that's fine, right? But we can't divide by 0. So a -5 is bad, so our domain is, and you could do this several ways. You could say all reals, comma, x not equal to -5. I'd be fine with that. Okay? Now you can also use our interval notation. Whoops, not that bracket. We could use our interval notation, which says we got -infinity to -5, and then we got -5 to infinity. Wouldn't that say everything but -5? Right? That would say everything but -5. I don't think it's good enough to just say x is not equal to -5. I think you ought to throw in the all reals except -5 kind of thing. Volume of a sphere. So in a story problem, and again, this is going to come up this year, and for sure it comes up. I know in calculus situations, we're getting real close to doing some problems that deal with volumes and so forth in calculus class right now. And one of the things we have to do is figure out the domain. Okay, what are our possible values? Now, what's our input on this function right here? What's our input variable? R, the radius, right? And so this is where we get into implied domain. If you're doing volume of a sphere, what are possible values of R? Can you plug anything you want in here for R? Positive, right? You can't have a negative radius, right? You can't have a negative. So in real life problems and story problems, a lot of times you got to think of it that way, right? That, okay, yes, in this equation, we could plug a negative in there. It'd be fine. But it doesn't make sense to have a negative volume, okay? So in this case, our domain would be 0. Well, I suppose you could have 0. I suppose, if you'd have no sphere, no volume. But I suppose you could include the 0. I wouldn't probably count it against you if you included or didn't include it, either way. Because you can argue, well, if the radius is 0, it's not a sphere. So you can make that argument too. But so either way, include or don't include the 0. Of course, you'd never include the infinity. Or you could say x greater than or equal to 0, or excuse me, not x, r greater than or equal to 0, or r greater than 0. Okay? Because negatives wouldn't make sense there. Okay, then what would you do for one like this? This has to be, so the way you want to work that is this. You want to show it like this. You want to say 4 minus 3x has to be greater than or equal to 0. Because it could equal 0. It's okay to do square root of 0. So that's okay, right? And then you would just solve it. So we take away 4. We divide by -3, which, don't forget, flips that sign. So x less than or equal to 4/3. Okay, would be your domain for that. Okay, so the two big ones. Well, so we one like this, and if it's a real life situation, think about what makes sense realistically. But when you have equations, the two big ones you're looking for are negatives under a square root and 0 in the denominator. Okay. All right, so you'll have some homework problems doing that. Got into that. Okay, I was going to show you one last thing. This is a calculus equation right here. This f of x plus h minus f of x all over h, and it's one of the first things, one of the early things we do in calculus, and it's where I really have to talk to the calculus class about function notation. Remember what it means. The German shorthand makes an appearance and everything. Okay, so let's take a look at an example of that real quick here. Okay, so write down this problem right here. Okay, write down this problem. So we have this function, and I want you to find this right here. Now this has a fancy sounding name. This is called the difference quotient. Now if you look at it real carefully, you would understand that it's really just a slope calculation is what it is. And that's, again, something that becomes a very important part of calculus that we do with this thing called the difference quotient. It's really a slope calculation. If you think about it, f of 3 plus h and f of 3, those are the outputs when you put in a 3 and a 3 plus h? Well, if the inputs are 3 and 3 plus h, the first point is 3, the second point is h units over, so 3 plus h, so that's 2 points. And so what we've done on top is subtract their y values, and on the bottom, if you subtract their x values, what would be 3 and 3 plus h subtracted? What would be 3 and 3 plus h subtracted? Would it just be h? Right? So the top is really subtracting the y's, the bottom is really subtracting the x's. It's really rise over run. It's really a slope calculation. But anyway, we call it difference quotient. Not important for you to know that right now. But for our next quiz, I might give you something like this and just say, here's f of x, you find this. Well, that's nothing more than plugging in, right? So let's do it. So now it's sometimes helpful to do this and this separately. So it might be helpful to just do f of 3 plus h. So let's just do that separately. What's f of 3 plus h? Well, remember, what's f of German shorthair mean? Well, back up. What's f of 2 mean? Do what? Plug a 2 in for the x's. What's f of 3? Plug a 3 in for the x's. What's f of German shorthair? Plug a German shorthair in for the x's, right? So what's f of 3 plus h mean? Plug a 3 plus h in for the x's, right? So we're going to have 3 plus h squared minus 3 times 3 plus h. That's it. That's all it means, right? So it's funny how f of 2 is easy, f of 3 is easy. It just means plug in a 2, plug in a 3. But all of a sudden f of 3 plus h is really confusing. And it shouldn't be, because it's the same thing. You take 3 plus h, you plug it in where the x's go. And so then we would FOIL this out. Now, you might need a little help here. What's 3 plus h squared? It's not 9 plus h squared. That's one of those algebra things we talked about the first day. It's 9 plus 6h plus h squared, right? You got to do 3 plus h times 3 plus h. Okay? And then we got to distribute this negative. So that'd be negative 9 minus 3h, correct? All right, now let's simplify that. The 9's actually cancel, which is nice. We get h squared plus 3h. Is that right? All right, now let's do f of 3. That we can just do in our head, probably. What's f of 3? F of 3 is actually 0. That's really nice. Okay, so now let's go over to here. So what's f of 3 plus h? F of 3 plus h we said was h squared plus 3h minus 0, right? Which we did here. Now a lot of times you'll get a number there or something, right? But we had, well, I guess 0 is a number, but you'll get something other than 0. Okay, and then what we have h on the bottom. Now we should simplify that. What can we do on the top? We can take out an h, which is actually helpful because then what? We can cancel an h. And so we end up with h plus 3. Okay? Now, what you don't know, and you have to tune in next year to calculus, right, to know why we would want to do that. Why is that interesting to us? Why would we care about that? Okay, but we don't want to muddy the waters right now and get into that. But that is something we have to do. We have to get down to there, and then we do some calculus stuff after. But it never fails that what throws us off when we work out this problem is the algebra part, right? That's what we got to do. All right. So I think there's one homework problem that's like that. Okay, the very last homework problem, it's like number 103. So my God, that's got to be a hard number. Problem 103, but it's not. It's just that. Follow that. Okay, so here you go. So there is a 96. A 96, you set up an equation. Okay, you set up an equation in 96, and then in part C it says use a graphing utility, and it's got a little graph symbol next to it. So in our book, whenever it has that, we use Desmos. So just go onto your Chromebook and use Desmos. And so part C, you graph it, and then part D, I think you answer the question based on the graph. Okay, on 96. Okay, 71 through 82, I think, is doing a bunch of domain questions. What's the domain? And then this means go by threes. Now, they're not multiples of threes, but just by threes. So 19, 22, hopefully you can all add 3, okay? 19, 22, 25, etc. Okay, so you get a mixture of some odds and some evens. Okay, and that's doing a variety of things that we talked about there.